with radical expressions. The quotes of the day today are in honor of Veterans Day yesterday. Um, the first one is a little hard of a quote to track down, but as far as I can tell, this version of this quote was from this guy, Richard Grenier. But it's basically a rephrasing of ideas from maybe Orwell and Kipling, but I like this phrasing better. We live in relative peace and comfort only because of rough men who stand ready, willing to do violence in our behalf. So we're fortunate enough that we can sit in our, comfortable houses with heat and air conditioning and everything and attend Zoom meetings. Maybe you don't consider yourself fortunate to be attending a Zoom meeting on math at 9 a.m., but still that relative to what some folks are dealing with around the world, I think we can consider ourselves quite fortunate. And another quote from John Adams. This is an excerpt from a letter of his, so the whole thing is quite lengthy, but I've edited it down and I think kept the general idea of the phrase. But he says, "I must study politics and war, that our sons may study mathematics and philosophy, commerce and agriculture, in order to give their children a right to study painting, poetry, and music." So, we kind of have to get the violence sorted out right first to secure society. And then we do the kind of, let's call them maybe logical things. So things like, how do we build up the resources of society, engineering, farming, these kinds of things. And then when we have enough resources in society and we have a surplus, we have the time to study painting, poetry, music, the things that don't directly contribute to things like biological needs. So, but that's not to say that they're any less important. If you've ever seen Dead Poet Society with Robin Williams, there's a whole great speech in there about, engineering and mathematics and things like this are worthy pursuits. They're incredibly important pursuits, but they're not the reason that we live. They're not the thing that we live for. So I think good quote by John Adams. The only thing that I would say is I think philosophy applies more generally kind of to all three of these regimes. Certainly to painting, poetry, and music and the study of aesthetics, but also to politics and war. There's a lot that philosophy has to say about that as well. So, but overall, I think gets at the core ideas that we need safety and security, and then the ability to provide for our needs, and then that frees us up to essentially do what we're doing now, to be able to, uh, to meet over Zoom and discuss things like rational exponents that them, for a lot of folks in the world would take a very significant backseat to their problems they're dealing with. Okay, so those were the ideas for today, and yeah, thank you to our veterans who helped make this possible for us. So 8.3, simplifying rational exponents. We started on this a bit last time. We're just continuing on with it. So recall that a rational exponent, something like, say, 4 to the 1/2 power, this is the square root of 4 to the first, or this would be 2. Or say something like 8 to the 2/3 power would be the cube root of 8 squared, or that's going to be the cube root. 8 is 2 cubed. 2 cubed squared is 2 to the 6th. And if I have, say, the cube root of, well, 2 to the 6th is like 2 squared cubed, I could write it that way. If I have the cube root of something cubed, I just get that thing. So a really quick crash course in what we talked about last time. So 32 to the 1/5 power, I can either think of this as like a 5th root of 32 and simplify that way, or I could work with it directly as a rational exponent. I might notice that 32 is 2 to the fifth, right? 2, 4, 8, 16, 32. So this is the fifth root of 2 to the fifth power, or just 2. Or I might recognize that 32 is 2 to the fifth power to the 1/5 power, and I have a power to a power rule that says I multiply the powers, 2 to the 5 over 5, 2 to the 1, which is also 2, of course. Okay, so let's go through a few more of these. So what about negative 27 all to the 1/3 power? Well, this would be negative 27, the cube root of that. If this is a number, say n, that's true if and only if n cubed equals negative 27. Is this a sensible thing to say about a number n, a real number n? And yeah, it could be, right? I could take a negative input, cube it, and get a negative output. That does work. So n is going to be negative something. And I see 3 times 3 is 9 times 3 is 27. So I think n is going to be negative 3 because negative 3 cubed, negative 3 multiplied by itself 3 times, does indeed give me negative 27 as an output. We do want to be a little bit careful with the details of our semantics, of our notation, and order of operations. Something like this, negative 27 to the 1/3, this is kind of like negative 1 times 27 to the 1/3. In other words, I have an exponent and a multiplication, P, E, MDAS. Exponents come first, so we would do the 27 to the 1/3 first. We would get a 3 with a negative. Here it does turn out that we get the same answer either way. That's not necessarily always the case, though. Then what if we add 27 to the negative 1/3? What does that mean? Well, we know that a negative exponent means I can flip it over the fraction line and make it a positive exponent. So that's 1 over 27 to the 1/3, or 27 to the 1/3, as we've seen above, is 3, the cube root of 27. So 27 to the negative 1/3 would be 1/3. Just kind of a coincidence that we have a 1/3 there and a 1/3 in the answer. All right, what about a similar thing with the 1/4 power? Negative 16 to the 1/4. In other words, the fourth root of negative 16. If that's some number, let's maybe say m, then this would say that m to the fourth equals negative 16. Can I find a real number m that when I multiply it by itself 4 times, I end up with a negative? Well, here this doesn't make sense, right? If m was a positive number, obviously its fourth power is going to be positive. If m was 0, its fourth power is 0. If m was a negative number, if I multiply it by itself 4 times, the first two factors multiply together, get rid of the negative, and same with the second two. If m is negative, its fourth power is going to be positive. There's no real number I can put in here to get a negative output. There's no real solution. Or at least as of this section, we'll see in a couple of sections, we'll change our point of view on this a little bit, but as of this section, this something like does not exist. Or if we wanted to be a little more specific, we'd say not a real number. For most of our math courses, we only deal with real numbers, including higher level ones, statistics or pre-calc or the calculus sequence. We really only deal with real numbers. So in those ones, we might say something like does not exist. But in this course, we're going to dabble a little bit into complex numbers and imaginary numbers. So maybe saying not real, not a real number is a little better practice for us. Now, something like negative 16 to the 1/4, remember, this would be like -1 times 16 to the 1/4. Well, this isn't so bad because I just need to simplify the fourth root of 16. And now I'm saying that m to the fourth equals +16. Well, this seems like a much more reasonable uh, thing to address. So what to the fourth power gives me 16? 2, 4, 8, 16. That's going to be -1 times 2. This is -2. If the negative is inside of the radical, inside of the rational exponent, then that causes a problem. Well, in this case, if we have an even root, if it's outside, then it's just saying the opposite of 16 to the 1/4 power. That's a different question. If we have something like 16 to the -1/4 power, again, this would just be 1 over 16 to the 1/4 power. 16 to the 1/4 power is 2. This is just 1/2. And 16 to the 3/4 power, again, I could maybe address this by saying, well, 16 is 2 to the 4th to the power 3/4. Well, if I have power to a power, I multiply the powers. 4 times 3 over 4, the 4's divide out. I have 2 cubed, or 8. Or I could think of this as the 4 in the denominator of the exponent tells me I'm taking a fourth root. Let me rewrite that so you can see the 4 a little better. There we go. And the 3 in the numerator tells me the power that the thing inside the root is raised to, 16 to the 3rd. Or this is the fourth root. 16 is 2 to the 4th. 2 to the 4 times 3 is 2 to the 12th. Or the fourth root, I want something to the 4th power. So this is 2 cubed to the 4th power, and the fourth root of something to the 4th power. This just gives me 2 cubed, or 8, as the answer. And lastly, if we want to look at this example, x to the 3/4 divided by x to the 7/4, here we would assume that x is non-zero, and we should also assume that x is positive because we have a fourth root that we're taking. So I could use my quotient rule. This is x to the 3/4 minus 7/4, or x to the minus 4/4 or -1. This would be 1 over x. Or another way to look at this is x to the 3/4 is the fourth root of x cubed. And that's over x to the 7/4, which is the fourth root of x to the 7th. Now the x cubed under the fourth root, there aren't enough factors of x for me to pull any of those out of the fourth root. So that kind of stays as it is. But x to the 7th, I could write as x to the 4th times x to the 3rd. There, I do have 4 factors of x that I can pull through the fourth root. It comes out as an x times the fourth root of x cubed. And I see I get fourth root of x cubed on top and bottom. They divide out. And leaves me with 1 over x. So I can work a little more directly with the exponents. as long as I'm careful with some of these nuances that we discussed above and last time, or I can work a little more directly with the radical form if I prefer that. Any questions on section 8.3? Okay, so moving forward then to 8.4 and 8.5, operations with radical expressions. So let's try to simplify this. Square root of 12 minus square root of 48. The first thing that we do not want to do is we don't want to make up algebra that's not correct. We don't want to say something like square root of 12 minus 48 or something like that. Right? This isn't going to work. It's usually more tempting to do this the other direction, but we don't want to do it this way or either. We don't want to do something like try to quote factor out the 1/2 power from the difference. Powers distribute nicely over multiplication and division. While multiplication specifically distributes nicely over addition and subtraction. So the distributive property takes us one level up or down on the PEMDAS hierarchy, but not two. So exponents or roots mixed with addition or subtraction don't coordinate so well. So we might look at this then and say, well, there's nothing that I can do. And that would be correct if I had something like, say, square root of 3 minus square root of 2. I really can't simplify that much, right? I mean, the best that I can maybe do is get a decimal approximation for square root of 3 and for square root of 2, and then subtract them and get a decimal approximation for the answer, but that's not the exact answer. This is about the best that I could do while keeping things in the exact answer. But I do notice that 12 and 48, those are kind of complicated numbers. They have lots of prime factors. Can I work with these to try to get the stuff under the square roots as simple as possible? In other words, I recognize that 12 is 4 times 3. Well, that's 2 squared times 3. And I recognize that 48 is 6 times 8, or that's 2 times 3 times 2 cubed, or that's 2 to the 4th times 3. And I just kind of, just as a side note, as a habit, when I write my square roots, at the end, I tend to like put a little tick mark over here. That's not for any particular reason other than in more complicated, when you're dealing with more numbers and variables and things. Sometimes if you had like square root of 2x, if your square root sign isn't, if it's a little bit too far over or something, it can be really hard to tell whether the x is under the square root or not. So I tend to put a little vertical thing there. It just, to my eye, it makes it a little easier to tell kind of where that square root ends. But so that's why I tend to write that. That's more just out of habit for this, for these applications. But I do see that I have 2 factors of 2 that can come out of the square root, make it 2 in front. So 2 times square root of 3. And then here I have 4 factors of 2, or this would be 2 squared squared. I have 2 factors of 2 squared that can come out as a factor of 4 in front. And if I had, 2 apples minus 4 apples, or 2x minus 4x, I would have -2 of whatever I'm counting. If I have 2 square root of 3s and I take away 4 square root of 3s, I'm left with -2 square root of 3s. So I see that I actually was able to simplify this because it ended up that when I simplified each of my radicals, each of my square roots, everything turned out to be square root of 3, and I was able to combine those as like terms. So if I have kind of the same base to the same power, 3 to the 1/2 power in each term, those are like terms, and I can combine them together. So it did turn out nicely here. There could be situations where it doesn't turn out so nicely. If I had the square root of 16 or something like that, I'd have like 4 minus 4 square root of 3, and there's not a whole lot I could do to make that any simpler. Okay, what about simplifying a product? So here I have 2 times the 4th root of 54 multiplied by -3 times the 4th root of 15. If I multiply these together, I know multiplication is commutative. So I have 2 times this root times -3 times this root. I can put all of my integers out front. 2 times -3 multiplied by the 4th root of 54. I cannot get OneNote to like my 4. There we go. And then times the 4th root of 15. Well, this is going to give me -6 out in front. And if I have 2 of the same type of radical, so these are both 4th roots, multiplied together, well, I can make that one radical. And OneNote really does not like my 4s today for whatever reason. So I have the 4th root of 54 times 15. Now, it is important that this property, square root of a times b equals square root of a times square root of b, or for cube roots or 4th roots or anything like that, only applies if a and b are bigger than or equal to 0. So particularly for square roots, for 4th roots, that kind of thing, this does not apply if either a or b are negative. The particular problem comes whenever both a and b are negative, then we don't get the right, we don't get the same thing on both sides of the equation. But we see that we have 54 and 15 under the radicals here, no problem. We can, in essence, factor out the 1/2 power from the product, is in essence what we're doing here, doing a reverse distributive property. And I could try to multiply 54 times 15, but I know that really my strategy is I want to break the component factors down as much as possible, try to isolate any 4th powers and pull them out of the 4th root. So 54 is 9 times 6, or that's 3 times 3 times 3 times 2, 2 cubed. 15 is 3 times 5. So 54 times 15 would give me 2 times 3 to the 4th times 5. Now, the factors of 2 and 5, there's not much I can do with those. They don't have enough factors to come out of the 4th root. However, my 3 to the 4th does have 4 factors of 3. That can come out as a 3. Oh, as a 3, -6 times 3 times the 4th root, and the 2 and 5 are stuck in there still. So I have -18 times the 4th root of 10. So to simplify radicals, I want to pull everything that I can out of the radical. If I have an nth root, if I have any factor to the n power inside of there, then I want to pull that out. And then if applicable, like up here, I want to combine like terms. So I want to get the number inside the radical, or radicals if there's more than one, as small as possible. And then if I want to, if feasible, combine like terms. So what if I add something like this? The cube root of 3 times 4 times the cube root of 9 plus the cube root of 18. Well, here, the cube root of 3 is just a real number. These numbers are all real numbers. I have multiplication, which distributes over addition. I can just apply a distributive property here. That's cube root of 3 times 4 times cube root of 9 plus cube root of 3 times cube root 18. Now we'll basically do what we did up here just twice, once in each of these two terms. So I have 4, let's see, 4 times the cube root of 3 times 9 plus over here I just have the cube root of 3 times 18. I don't know why I'm writing so small today. But I see the cube root of 3 times 9 is 3 cubed. Cube root of that is 4 times 3. And the cube root of 3 times 18, well, 3 times 18, 18 is 9 times 2. So this is going to be 2 times 3 cubed. This 3 cubed comes out of the cube root as a 3 and cube root of 2. So this is going to simplify down to 12 plus 3 times the cube root of 2. Any questions so far? Okay. So let's take a look at this next example. Here we have something that's similar in nature to this one up here. I have some roots that are multiplied together up here, and I saw how that worked. What about roots that are divided? Similar strategy. The cube root of 24 divided by cube root of 81. We can, in essence, factor out that radical. We can do a reverse distributive property. And we have cube root of 24 divided by 81. I can do some simplification here. I know that 24 is 3 times 8. And I know that 81 is, well, that's 9 times 9, or that's 3 to the 4th, or that's 3 times 3 cubed. My 3's divide out. Inside of this radical, I can do all kinds of simplifications, just standard stuff, dividing out common factors from top and bottom, or adding or subtracting. If I'm inside the radical, then all of my arithmetic works just like like we had previously seen before we started talking about roots and radicals and rational exponents and all this. And I see that this is going to be the cube root of, well, 8 is 2 cubed. So 2 cubed over 3 cubed, well, that's 2/3 cubed. Again, by kind of a factoring property. Or this is going to be 2/3. That's my answer, 2/3. I could have chosen to do this a different way. I could have alternatively simplified each of the cube roots. 24 I recognize as 3 times 8, and 8 is a nice perfect cube. And 81 I recognize as 9 times 9, or 3 to the fourth, or maybe 3 times 27. Or this is 2 times the cube root of 3 divided by the 27 comes out. 27 is 3 cubed. So it's 3 cube root of 3. And I see I have a common factor in numerator and denominator of a cube root of 3. It's a bit of a strange looking common factor, but that's what it is. In numerator and denominator, in both cases, I have something multiplied by cube root of 3. It can divide out and give me 2/3. Either approach that I want to take, I think either one is equally valid. Okay, what if I wanted to simplify something like this? This looks really complicated, but if we take it piece by piece, it's not so bad. So the first thing that I recognize is that both of my roots are the same kind of root. That's a cube root over a cube root. If I had like a cube root over a square root, this would be a lot more difficult to work with. But I can, in essence, factor out that cube root. 54 x to the fourth, y to the negative 2, over 16 x to the negative 2, y to the fourth. Oops, y to the fourth. Now, there are a couple of ways that I could go about this. I think probably the easiest approach is to try to write all of my exponents as positive exponents. So I think that's the first thing that I'm going to do. I have a 54 on top, a 16 on the bottom. I have x to the fourth on the top, x to the minus 2 on the bottom. This x to the minus 2 on the bottom becomes an x to the plus 2 on the top. Right, so let me just do this really quickly over here. Just looking at the x bits, x to the minus 2 on the bottom becomes an x to the plus 2 on the top that's multiplied on. And if I have the same base multiplied different powers, I add the powers, x to the sixth. And on the bottom, if I have a y to the negative 2 power on the top, that becomes a y to the plus 2 on the bottom, or a total of y to the sixth on the bottom. Now 54 over 16. Well, I guess I do have a factor of 2 in both of those. So 16 is 2 times 8. And 54, well, that's what, 2 times 27, I think. And I recognize that this is the cube root of a bunch of stuff that's perfect cubes. 3 cubed times x squared cubed, that's what x to the sixth is, over 8 is 2 cubed times y squared cubed. All of this stuff can come out of my cube root, giving me 3 halves from the numbers, and then x squared on the top over y squared on the bottom. And if I wanted to be really careful here, because I have like an x to the minus 2 here, I don't want to say x cannot be 0 and y cannot be 0. Y not being 0 is still implied in this end expression, but x not being 0 is not directly implied. But we can't have x being 0 because of this bit here. In this radical, we have an x to the minus 2 of 1 over x squared, and that wouldn't make sense if x was 0. So we might want to include this for clarity. Any questions so far? Okay. So let's look at this example, rationalize the denominator and simplify. So what does it mean to rationalize, say, a numerator or denominator? Well, what it means is to get rid of the radical. So rational numbers are things that are like fractions, or of course, whole numbers and integers are fractions. They just have a denominator of 1. So take that square root of 12 and make it look like an integer. So I want to know square root of 12 times what gives me an integer. I guess I could multiply by square root of 12, right? If I multiplied by square root of 12, this gives me 12. That would be easy enough. I could do that. But then what would I end up with? I'd end up with 3 square root of 12 over 12 if I multiplied by square root of 12 on the top and bottom. But that radical, the square root of 12, isn't really simple, right? It has a bunch of extra factors in it that I really don't need. Can I find something better to multiply by? Let me do a little bit of simplification first and see where I end up. So square root of 12, well, that's square root of 4 times 3, or 2 squared times 3. I could write square root of 12 as 2 square root of 3. Right. There's my 2 squared. And it comes out and makes a single factor of 2 in front of the square root. Well, now I can see that I just multiply by square root of 3 on the top and bottom. And in the denominator, I have square root of 3 times square root of 3 is 3. My 3 is actually divided out here nicely. And I end up with square root of 3 divided by 2. So before I go rationalizing, maybe it would make sense to simplify as much as I can. What about something like 15 over the cube root of 9? Well, the cube root of 9 is the cube root of 3 squared. There's nothing I can really do to this radical as it stands to simplify it. Now, I suppose I could take a similar strategy to up here. I had the square root of something. If I multiply by the same thing, I have the square root of something squared. And then that gets rid of the square root. I guess I could multiply by like cube root of 9 and then cube root of 9 again. But that seems like a bit overkill. Really, I see I have 2 factors of 3 inside of my cube root already. If I can only pick up 1 extra factor of 3 inside the cube root, I would have the cube root of something cubed, and I'd be able to get rid of my cube root. So if I take cube root of 3 and multiply that on, then I have the cube root of 3 squared times the cube root of 3. That's the cube root of 3 cubed, or just 3. So if I multiply the denominator by the cube root of 3, I'll be able to simplify this denominator, get rid of the root in the denominator. But if I multiply by cube root of 3 on the bottom, I better multiply by it on the top as well. So 15 times cube root of 3 on the top. And the denominator, I have cube root of 3 squared times cube root of 3, or that's cube root of 3 cubed, or just 3, which gives me 5 times the cube root of 3 as my answer. Any questions on that one? Okay, and now I want to do the same thing down here, rationalize the denominator. So if I think of the fourth root of 7 over 32 as the fourth root of 7 divided by the fourth root of 32, it's a little more clear what I'm asking for here. I want to get rid of that fourth root of 32. Well, I know that 32 is 2 to the fifth, or that's 2 times 2 to the fourth. If only I had another 3 factors of 2 to combine with this one and make another 2 to the fourth, I could get rid of my fourth root. So I would like to pick up 3 more factors of 2 to combine with this one to make another nice fourth power. Or I would want 3 more factors to make this 5 to increase it up a few numbers until it became a multiple of 4. So I need to multiply by 2 cubed, or 8, under the radical. I want to multiply top and bottom by the fourth root of 8. In the numerator, I have the fourth root of 7 times 8. Well, 7 just has, that's a prime number. It's just one factor of 7. 8 has 3 factors of 2. There's nothing that can simplify here. So I'll just write that as the number 56 over the fourth root of 32 times 8. Or instead of writing it that way, I'll choose to write this in powers of 2. It's 2 to the fifth times 2 cubed, or 2 to the 8th. So that's the fourth root of 56 divided by fourth root of 2 to the 8th is 2 squared, or 4. So my answer, fourth root of 56 divided by 4. Give me one sec here. Okay, any questions up to this point? All right, now let's look at a more challenging question. Every denominator that we've looked to rationalize so far has just had a factor that was a radical in it. If I try to do something similar, if I try to take a similar approach here, I see the square root of 10 on the bottom. Maybe I want to get rid of it. If I just try to multiply by square root of 10, well, my denominator then becomes 3 times square root of 10 minus 10. I just kind of like switched which term the square root of 10 is on. So that doesn't really help. All right, so what do I need to do here? I need to find something to multiply by that gets rid of the square root of 10 but doesn't introduce it anywhere else. What would be really nice is if I could just like square all of my terms individually. If I could get like 3 squared minus square root of 10 squared, like that, something along those lines, that would be really nice. Because then even if I had like a square root of 2 minus square root of 10, even if I had different, well, that's maybe not a good example, say square root of 3 minus square root of 10, I could square everything, square each term individually, and get rid of all of the square roots. So basically I have a minus b, and I want to multiply by something to get a squared minus b squared. I think I recognize this pattern, the difference of two squares pattern. Well, a squared minus b squared is a minus b times a plus b. So if I have a minus b, and either a or b has a square root in it, or both, if I multiply by a plus b, multiplying by this kind of conjugate, just changing the sign on one of the terms, then each of the terms individually gets squared. Note that there's an analogous situation where if I had, say, 3 plus square root of 10, then I multiply by 3 minus square root of 10 and get the same kind of result. So 4 plus root 10 over 3 minus root 10. I want to multiply by 3 plus square root of 10. I did that on the bottom. I better do it on the top as well. And I have to be careful with the top. This 4 plus root 10 is like all one factor on the top that I have to multiply by 3 plus root 10. On the bottom, my firsts give me 3 times 3 is 9, or 3 squared. My outsides give me plus 3 root 10. My insides give me minus 3 root 10. Those go away. So my extra root 10s that I pick up, I've engineered it so that they exactly cancel out and go away. So I have no square root of 10s left. And then my last give me minus root 10 times plus root 10. That's a minus. Root 10 times root 10 is 10. What does my numerator give me? I can't get rid of the square roots altogether. I can just choose to put them all in the numerator or all in the denominator if I want. That's what we're doing here. My firsts give me 12, 4 times 3. My outsides plus 4 root 10. My insides plus an additional 3 root 10. That's plus 7 root 10. And then my lasts, root 10 times root 10 is plus 10. Or overall, I end up with 12 plus 10 is 22, plus 7 root 10 over negative 1. And here I can simplify this a little bit further still. Negative 22 minus 7 root 10. And I think that's about the simplest I can go. I don't remember if I explicitly said it, but 10 factors to 5 times 2. Each of those only has one factor, so we can't simplify the square root of 10 at all. So that is the best I can do. Negative 22 minus 7 square root of 10. Any questions so far? All right, and let's look at one last problem. This is a more difficult looking problem than the previous one because we have more square roots floating around. But we might actually realize the strategy is pretty much the same. So I have square root of 24 minus square root of 27 over square root of 12 minus square root of 3. Now I could go ahead and multiply by square root of 12 plus square root of 3 on the top and bottom, rationalize by denominator that way. That would work. At the end, I would have a lot of simplification to do. I might actually realize, just looking at this, that, I mean, square root of 3 is pretty simple, but square root of 24, square root of 27, and square root of 12, it seems like there's a lot of factors in those. Let me try to simplify each of these radicals a little bit. Square root of 12 is square root of 4 times 3. So square root of 4 times 3. This 4 can come out of the square root as a 2. It's actually just 2 root 3. That denominator is actually going to simplify quite a bit. Right. I think, a few weeks back, we talked about managing complexity. Like, you'd rather your complexity go like this than like making it really complex and then trying to come down the other side and simplify. So we're going to take the time to simplify at this first step, and we see we actually get a really nice simplification here. 2 root 3 minus root 3 turns out to be just root 3 on the bottom. So I save myself a lot of hassle of multiplying by root 12 plus root 3 on top and bottom, multiplying out, simplifying, and all of that. That would have been quite a bit of effort. So simplifying first saves me that extra complexity. Let's look at the numerator. Root 24. Well, 24 is 6 times 4, so that's 2 root 6. 6 is 2 times 3. We only have one factor of each of those prime numbers in there. Nothing much more we can do there. So this is going to be 2 root 6. And square root of 27. This is 3 cubed. So this is 3 square root of 3. Two of those three factors of 3 can come out of the square root, making a 3 on the outside. And one of them is stuck inside without a twin factor to go with it. So I have 2 root 6 minus 3 root 3. I'm looking to get rid of this root 3 on the bottom here. I actually kind of noticed that I have a root 3 on the top in the second term. I also kind of have a factor of root 3 in this first term. Root 6 is like root 2 times root 3. I can actually factor out a square root of 3 from both of those terms. From 2 root 6, that's 2 times the square root of 2 times the square root of 3. And the minus 3 root 3, obviously there's a factor of square root of 3 there. I can actually just divide this out, leaving me with 2 square root of 2 minus 3 as the answer. I actually didn't have to do any of this multiplying by the conjugate or simplifying or anything like that. I'm just going through the steps and simplifying things piece by piece. We ended up with a really nice result. We probably wouldn't expect this, right? I mean, I'd have expected to have to multiply by the conjugate. But even if I was going to multiply by the conjugate, I want to simplify as much as I can first. See if anything divides out, see if anything simplifies, and it'll make the rest of the problem that much easier to do. Any questions on anything from today? Okay, so that wraps up a 3, 8, 4, and 8, 5. One little side note, I suppose. I'm not exactly sure why, but folks make a big deal about rationalizing the denominator. It does make the thing look a little nicer because you have just kind of one square root floating around instead of a couple of them. Or maybe another, you have fewer square roots floating around anyway. One instead of 2 here, or you could have another square root on the top, I suppose, as well. As far as just specifically rationalizing the denominator, I don't know how much, value there is in doing that for its own sake. So you might say, like, why are we doing this? Why do we call this simplest form? I mean, is this really like all that much simpler than this? Especially if we say ended up with an over 3 or something like that. I mean, we kind of had a nice result here where we ended up with over -1 and could get rid of that. But is this, if I had -22 minus 7 root 10 over 3, is that all that much nicer than this one? Maybe not. However, this idea becomes really important in complex numbers. We can take a complex number like a plus bi that we'll see in a little bit here. If I have the ratio of two complex numbers, it can be written as another complex number. So the complex numbers are closed under division, and that's where this really comes into play. So we're doing this. I mean, it might seem like a bit of a silly thing to do here, but it is actually quite important in a couple of sections. So just a little side note on that. I sometimes feel like folks make way too much of a big deal about this is the simplest form. And I mean, this form isn't all that much better to deal with than that form, but really what we're doing is we're kind of practicing for the complex numbers when we see that the quotient of two complex numbers is itself a complex number, and that's a really important property of the complex numbers, that they're closed under the standard arithmetic operations. Okay, so that finishes up our discussion for today. When we come back, we'll just continue working through chapter 8. Let me stop the recording.